Hello, everybody. Can you hear me?
Yes, we can hear you clearly.
Okay, awesome. Awesome.
Maybe
So,
turn on
guys,
your video. Um,
what's that?
Maybe turn on your video. That might be nicer. If you,
Okay, one
yeah,
second.
if that's
Okay,
possible.
cool. Yes, sorry about that. Hi, guys. Again, welcome to the third tutorial we have here. And in this tutorial, I wanted to show that how do we use ScaleSim as a library to create your own simulators. I mean, this is just again logistics that check your Python version that is Python 3 and then install ScaleSim as a package. So basically, if you just follow the steps which Moritz has told you in the previous tutorial, that would suffice. And in this thing, we are not going to make any changes to ScaleSim per se, but we are going to write our own code and then bring in libraries or APIs from ScaleSim to do some heavy lifting for our code. All right, so what we will cover in this tutorial are the following. So first, I wanted to give you a high-level description of what we are trying to achieve, what the simulator is supposed to do. Then I'm going to build the simulator. So by quote unquote building, I mean that I have already built it. I took out some code snippets out of it, which is the partial tutorial, the partial simulator and the snippets are in the file. If are in this tutorial 3 folder, if you have downloaded a zip file from our web page, but that's okay if you did not, because I'm going to repeat this steps here. And then after the simulator is built, hopefully it does not have any typos or anything. We are going to simulate the runs, do some simulation run, and then we'll do a general discussion. And I would love to hear your thoughts about what do you think about using this ScaleSim as an API, and what are the other features that would you need so that your own simulation building could be fast and more less painful. So with that, let me get started with the high level description. So we are going to create a small distributed systolic array setting simulator. So we have four of these units where each of the unit in this distributed thing is a systolic array, which will be which computer memory of which we will leverage from ScaleSim. And then all of them kind of put their accesses together and they talk to off chip. So that's just an assumption. And then the dimensions of each of these arrays are basically same as tutorial 1. So we are using 64 cross 64 arrays. Each of them have 512 KB of buffer size. So total buffer size is 1.5 MB. And then the data flow, which is run on each of these arrays, is output stationary. Sure, we can use wait stationary, input stationary as well, but output stationary is just one demonstration. So nothing special about it, actually. Okay, so we are going to examine 3 logical layouts. So first is a very obvious, which is a 2 cross 2 grid. So what happens in a distributed setting is that when you have these different accelerators, you kind of go ahead and partition the input workload or the generation of the output workload such that multiple things can run in parallel and you can get more parallelism. So in this case, what we will do is we will cut the input in half, cut the filter in half, and send the send respective parts of the input and filter to the respective arrays. And as you might have noticed over here, there is a bit of replication of data. For instance, the same input goes to both the arrays on the top row, and the same filter goes to both the arrays on the first column, and so on and so forth. But that is expected in distributed simulated setting. So then obviously there is a trade-off of how much input or filter you want to distribute. So there are multiple ways of logically laying out these arrays. So another one of them is like 1 cross 4 layout, where you do not redistribute the filter. You kind of just partition the filter and then send the filter parts into the respective arrays and replicate inputs anywhere, or the other way around where you just replicate the filters and not replicate the inputs at all. So with that, the metrics of interest for us is that how is the performance, what is the mapping efficiency, and what is the object how much does the object access look like? Well, in this tutorial, I'm just going to look at performance just because of time restrictions and to keep things simple. But Scalesim reports all of these metrics, so it's very easy to get a sense of overall mapping and object accesses. So now the main part of the tutorial, that is building the simulator. So I just wanted to show the implementation plan for this thing. So obviously, like if you are trying to reuse some existing library, our objective should be maximize code reuse. We want to write as little as possible. So the scale out simulator should just be some wrapper scripts over the libraries which we import. So in this particular flow, what we do is for input processing, we are taking inputs in the same format as you would do in ScaleSim. With a little bit of extra information, right? How are you arranging the arrays and how many number of arrays you have? So most of the input processing is done by the topology util and the scale config classes, which is already present in ScaleSim. Then the compute part. So compute part is where your ScaleSim tool kind of creates the operand matrices. So it sees that, oh, what should be, how should the how should the rows and columns of the input, output, and the filter should look like. So that all computation is done in operand matrix creation, which we also take from ScaleSim. And then this partitioning of the operands, so allocating the different rows and columns of these inputs are something which we have to do because ScaleSim does not have any libraries for partitioning the operands. So this is a custom processing, and we will implement this custom module in the simulator. And then mapping. So once you have partitioned the operand, now you have to run each of the systolic array. So within each of the systolic array, with the operand which we have got, we have to figure out how to map it properly with the given data flow. So that is what, it is also done in ScaleSim as well. So since we are using output stationery over here, we are just using the systolic OS class to do the mapping. The next, once the mapping is done, now we have to make sure that the memory requests are serviced properly, and we can directly use the double buffered memory classes we have in ScaleSim to do that. And finally, the report generation, like the double buffer memories and everything, will generate the cycle counts and the access counts, and also other, like the systolic OS class and the operand matrix class. They also give some intuition on the compute, utilization, and everything. So those pieces of information needs to be mixed together to form a coherent report, and that we have to do. That is a wrapper script we have to write, and then finally we get the report. So what we see over here is that out of these 6 major components, 4 of them we can directly take from ScaleSim. We don't have to write anything for that. And that means that we have almost 70% module reuse. And obviously the partitioning and report generation is not as complex as just doing the mapping or memory servicing or even generating the operand matrices. So you have like 90% of the work done by the existing library over here. Okay, so now I would just go through the different code inputs we need to do. So so if you are following along, right, and if you have access to the tutorial 3 file and the tutorial 3 code snippets, so just look for these numbers like blank 1, right? So for instance, this is my ID over here. So if I look for blank 1, sorry, blank 1. Yes, so it's over here at line 61, right? So in line 62, I just go ahead and put this code over here. So what it essentially doing is it's invoking the input processing classes of scalesim. So for instance, topology, to read the topology, we have the topologies class. To read the configuration, we have the config class. And then we are passing the topology file name and this config file names, and it is reading and processing those inputs. So let me just quickly copy this and paste it over there. Yeah, Zoom is taking all the juice out of my computer. So sorry about all the delay which you see in copy and pasting. Okay, so that now is copied. So let's go to the next step. So now the next step from after the input was creation of the operand matrices. So I'm just going to insert this code in the blank too. But what it essentially does is now since you know what the single array configuration looks like and what the topologies we have. So for every layer, it generates the input feature map, filter, and output feature map operand matrices. And we are just going to call the library, the API in ScaleSim to do that. So let me just quickly copy and paste this code as well. So I will, if you're following along with me in coding, just search for blank two. So blank, oops. Oh, I think I just blank two. Right, there it is. So I will just copy and paste this code over there. Okay, so there we have. So now we have done the second module instantiation, which is generating operand matrices. And then what I have implemented in code is this, if you can see where my mouse pointer is basically GIF of my parts. So this is a custom implementation to slice and dice the operand matrices generated. I would not go much into detail into it because it will take a lot of time, but you can kind of understand that we are taking out chunks to map into each of the four arrays, depending upon the data flow, which is output stationary for our case. Okay, so after that, next we have to instantiate the compute system. So the compute system basically now takes the operand matrices and then creates a mapping so that it can generate requests for the memory. So to do that, I will just copy and paste the code for blank 3. So blank 3 is right over here. I'll just do it. So by default, we are using output stationary for this particular demo. But the code, if you want to run this code sometime, this code does support the other two data flows as well. So feel free if you want to play around with the code and let me know what you think about it. Okay, so finally, once this is done, finally we have to get the memory system in here. So in blank 4, which is over here, like somewhere in the bottom there. So what we will do is we will instantiate the code for memory system. So I will just go line by line what this code is doing. So it instantiate one memory system. It calculates the buffer sizes from the config file which we have given. And by the way, this is memory system for just one of the subarrays. And there is a for loop which will instantiate all the same memory system for all the different subarrays. And then what it just does is uh, it goes ahead and then sets up the memory system. And then finally, whatever demand matrices are generated by the mapper, it just services them and to create the traces. So let me just quickly go and paste them. So there it is. And, oops. Okay, so there it is, blank 4. Let's just paste it over here. Cool. So now our simulator is complete. If only it was that easy, but that's cool. So now it is done. So let me just go ahead and start a run. All right, so I will do Python. Something is wrong in here. Okay, that's not right. Okay, Python tutorial 3.5. And now it will, so there is, so it will run all the four, the runs for all the four different subparts, and then will report, uh, will generate a chart to report what it finds. But before it does, let me just show you the results from my pre-existing runs. And oops, I think I made a typo. Oh, then that's why. All right. Okay, so when we look at the runtime and utilization, we see very interesting trends. We see that there is the 4x1 clearly wins, and the reason for this is the size, the mapping, and the dimension of the input workload. And you can see that for this workload in a 4x4, we get like 80% of the overall utilization. And then depending upon what your utilization is, so for instance, 1x4 has very low, like 20% utilization. It takes a large amount of time to actually run. And then for 4x1, and then for DRAM accesses, what we can see that 4x1 is better in terms of DRAM access as well. And in my opinion, this is due to the fact that there is less replication in 4x1 as compared to 2x2 and 1x4. So because of the input feature map, especially in the input feature map, we see that there is a tremendous savings in the number of accesses due to the DRAM in this particular configuration. And this directly translates to energy efficiency. So that was there for this tutorial. I will just wait for this run to complete, and in the meantime, if you guys have any questions, just feel free. And also after this, so this was a final tutorial. So I think we have a lot of time left in here. So if you have any questions or want to do any discussion, I'm open for it.
I have a question. Can you please like do the slides for, yeah, this is slide.
Mhm.
So there is like a utilization, right, on the right side, and um, so how like the when we have like the for the 4-to-1 case, right? So we have less utilization, but we have also less number of cycles in means that it's faster, right?
Oh, this one?
The last bar.
Oh, I'm sorry. So this one, the utilization is this a dashed line. I
Oh,
apologize.
okay.
I did not put correct markers for it. That's just my mistake. Here, I just wanted to show that it has the lowest runtime because it has the highest utilization.
It is. Okay. Yeah,
Yeah,
I couldn't follow that the red one is actually the utilization. Yeah,
yeah,
I,
it's totally my mistake. Yeah, I should have put the legends over here. But thank you for bringing that into notice. Are there any more questions? Or what do you guys think? Do you have any suggestions? I will be very happy to hear about them.
I think yeah, that's very cool that like the idea of having like multiple grids. One thing that is probably interesting to see like how so when you have multiple the parallelism in terms of like having multiple systolic arrays, how what's your strategy to like adding to parallelism to the memory subsystem? Because um, if you have, let's say, be able to have multiple configuration for the memory subsystem as well, and how you doing like similar to the computation, how you doing this hierarchy of memory levels for each grid and how they communicate and how they um, you know transfer data between each other. I mean, that's something that is also like interesting to me to see. Like, in those systems.
I see. So basically, you want the memory system to have to be more richer in terms of different configurations, right?
Yeah. So I don't know if you're in your current design, like can, so each grid has its own, let's say, memory SRAM, or is it like one big like SRAM for each all the grids?
No, it is. Let me go back to the slides. I might have just rushed through it. So each unit kind of looks like this, right? So, oops, sorry. So each unit looks like this, which means that it has its own set of SRAMs. So let's say this is the SRAM for filters, this is the SRAM for input feature map, and this is the accumulating SRAM. And each of them have a separate site. And so this dimension is for this only one unit. So the total SRAM capacity of this thing would be 1.5 into 4, which is 6 MB. And then so scale sim only works in this particular realm, but when you are making a simulator, let's say you put another SRAM over here, I think that is pretty much doable because you just need to instantiate a top level memory module like what Moritz kind of did, right? Like it had a back, so L1 had a backing buffer to L2. Now instead of just that, you have a shared L2 between all these arrays. So that is doable, but we haven't done that yet. So maybe, I mean, of course, anytime you add any feature, bugs and everything would come. So this, I kept this tutorial pretty simple, but you can do that with this, with the library
And
you have.
are you envisioning like a system that like each of those systolic array potentially can communicate through a network? Like, are there any like, I mean, data sharing between each of these grids potentially can you can take advantage of like communicating between those different grids?
So that's a very good question. For this tutorial, no, but for a future simulator, yes. I mean, I do not, I have not started working on it, and I do not know that if it is in the current roadmap, but it is definitely a very interesting idea to play with, right? And if you guys have a requirement for such thing, right, it would be good that it would be very nice that if there are some codes coming from you folks, and then I would try to bind it as much as possible, because scale right now is just a single simulator, so I wanted to make it more versatile. And then later, I think it would be very interesting to see how it pans out as we go explore the scaled out configuration more and more.
Yeah, thank you.
Yeah, thanks for the questions. And it's very interesting ideas. So if you end up using ScaleSim in your project, I would be happy to answer your queries if you raise them in using the GitHub issues or with anything else.
Sure.
Yeah. Um, so if I mean, feel free to like put your queries up in the Clouder platform as well. But if nobody has a question, then we can just wait for a few more minutes for the run to finish, and then next. So we wanted to do a discussion and tell you some of our roadmaps and everything from 1:30 to 2. So we can feel free to join again at 1:30 just to for this discussion. I think it would be good for us to know what you guys really want, like Mohammed Reza is told right now, and yeah, and knowing your thoughts is always good.
I've, uh,
Yeah, Maurice, did you say something?
yeah, I just wanted to say that I've made a slide for the break. So if you stop sharing, I can just share that, but you still probably want to show the final result
Yeah,
of the run, right? Yeah.
I think it would just take like a few more seconds to finish. Uh, yeah, I think Zoom is taking out all the juice out of the
Yes, it
system.
was the same for my PC. So
Yeah, it's usually a few seconds. Like the one with 30 seconds probably just took me 10 seconds before.
mhm.
Like, yeah. Oh yeah, so this is the same plot for the runtime and utilization. And if I close this, then it gives the plots for DRAM accesses. And yeah, you can see the Fortress one wins because of the big blue lines in everyone. Okay, so I will stop sharing now and I will also stop recording. I'm available here. So if you have any questions or comments, just unmute yourself and tell me.